Okay, welcome to the unit review. This is going to be on properties of water in that functional group PowerPoint that we saw on either Thursday or Friday during the first week of school. So if you see all these notes that are dealing with maybe logistical stuff in the classroom, don't worry about that. All we're doing right now is just talking about content. So in preparation for your exam, I'm going to let you know what the things that you should really focus on. Now, I know if you have no background in chemistry, this was a really dense PowerPoint for you, and I want to assure you that it is not going to be like this all year, okay? I promise you, it's not going to be like this all year. This is really dense conceptual stuff from chemistry that if you didn't have AB Chem or Chem Honors, this was a little tricky. But as we move through the year, you'll see that it really is a biology course. It's not a chemistry course, and we don't have to panic on that front, okay? So let's go ahead and get started. So by the end of this, I really need to make sure that you can understand, and here's a really good study tip. When you are studying, go back to these pages where I tell you what I'm looking for. What does it mean for a bond to be polar or nonpolar? If you can't say that out loud using English, then you are probably not at the level that you need to be for your exam. If you can, then you can check that off and say, okay, I'm good studying there. I also need you to understand how water's polarity contributes to its unique properties. So when we start talking about adhesion, cohesion, specific heat and surface tension, you'll see a little bit more of that in AP Classroom, not so much in this PowerPoint. You need to be able to understand hydrogen bonding. What caused that? What is it actually at the subatomic level that was causing that, right? What are the conditions required for a hydrogen bond? We need to be able to define adhesion, cohesion, and capillary action. And then we also need to understand the certain structures and how they're going to dictate function. That's a theme in biology we're going to see all year. Structure dictates function. We're starting to talk about it now, but we will see it all year. So keep that in the back of your mind as we're going through this entire curriculum. So we're going to move past that because that was in our class. But I want to remind you that chemistry is king, that ultimately everything comes down to atoms and how they interact with each other, and that is ultimately going to build molecules, and those are going to act a certain way. And so we really need to understand the foundation, which is, of course, the atom. And here we have a carbon atom. How do I know it's a carbon atom? Well, because the feature that defines an atom is going to be how many protons it has. So if you look at your periodic table, you will see that carbon has 6 protons. And if you don't know where that came from, the little number in the top left-hand corner for each of those elements tells you how many protons there are. It's called the atomic number. So if there are 6 protons, well, protons have a positive charge, electrons have a negative charge, and overall my atoms on the periodic table are going to be neutral. So if I have 6 protons, I need to have 6 electrons so that it cancels out to a ultimately 0 charge on that atom. So here we have a carbon atom. Because it has 6 protons, it's neutral, so it has 6 electrons. I'm not allowed to change the identity of an atom, so I can't add a proton because then suddenly I would have nitrogen. I can't lose a proton either because then suddenly I would have boron. And if we did that, then we would be really rich because we could turn elements into other elements all the time, right? And so we'd all turn things into gold or silver, but we can't do that. Instead, what can happen is electrons can change. The number of electrons can change. So if I lose an electron, well, electrons are negative. So if I lose an electron, then my overall charge will turn positive because I have 1 fewer negative charge than I had before. If I gain an electron, then I have 1 more extra negative charge, so I'm going to have an overall negative charge on my atom. We have terms for this. If it is positively charged, it is an ion, specifically a cation. If it is negatively charged, then it is going to be an anion. Okay, so if we can get that, then we're ready to move on to talking a little bit about other things like bonds. So the periodic table is a periodic table of elements, aka these are just atoms, but I'm not just one atom, you're not just one atom, you're a really complex structure that's made up of lots of molecules. And these molecules are made by bonding atoms together. Well, we hear that term bond all the time, but a bond is really quite specific in its definition. It is a shared pair of electrons. It is a shared pair of electrons. So, when we are dealing with molecules, not all atoms are going to want to bond in the same way. Some atoms are going to want a lot of bonds and some not so many. So, let's take carbon for example. Now we spent a little bit of time in class dealing with the valence shell and figuring out how many bonds carbon wants to form. And we do that because in biology, carbon is really the foundational atom. But I'm not going to ask you for that explanation on any sort of exam, so I don't want you to worry too much about it. Instead, we can use that shortcut that we talked about. On the periodic table, I told you that these atoms are sort of trying to become like the noble gas. Well, if we look at our periodic table, it would be very wise for you to have a periodic table for this discussion, right? If you look at the periodic table, carbon is most close to neon as the noble gas. So the closest neon gas to carbon is neon. So what carbon will do is it will form 4 bonds so that it will look like neon. And again, that comes down to the idea of valence electrons, but we're not going to talk about that because it's not something that I'm going to ask you on any sort of exam. So if you look at where I'm talking, I will show you the periodic table, although this is not the most perfect demonstration, but carbon is right here. Carbon wants to look like neon, so what it will do is it will gain as many bonds as it can to look there. So we can gain 1, 2, 3, 4 bonds. The other trick here is neon's atomic number is 10, carbon's is 6. So if we subtract the 2, that is 4. If I want to look at oxygen, another biologically relevant atom, well, oxygen is 2 away from neon, 1, 2, and so it wants to make 2 bonds. And you can do that for all of these. I will let you know that you are more than welcome to explore that on your own, but it is a little bit beyond the scope of biology and more appropriate for a chemistry class. So if you're really interested in it, I highly recommend taking chemistry. It is a wonderful course. Okay, so we know that a bond, by definition, is a shared pair of electrons. So 2 electrons being shared between 2 atoms. That is one bond. But it turns out that not all bonds are created equal. Some bonds, those electrons aren't evenly shared. It's not like exactly in the middle between the 2 atoms. Instead, some atoms are a little bit selfish. So oxygen is a little bit selfish compared to hydrogen. And that is the case in water. So oxygen holds on to these blue, let me see if my pointer, so these blue dots here are electrons, and you can see that they are held much more closely to that oxygen atom compared to the hydrogen. Well, recall that electrons are negative. So if electrons are negative and we have all of these negative charges hanging out around oxygen, well, now we have a negative charge around that oxygen. Now, hydrogen hasn't totally given up its electrons, but it has mostly given them up to oxygen. And so we call these charges partial charges. So this oxygen would have a partial negative because these electrons are very close to the oxygen. And the hydrogen, because it's given up that negative charge, relative to what it was before, it's more positive. So we use partial positives and partial negatives. This symbol here looks like an S that comes around. is a partial symbol. So if you see that, that means that there is a partial negative and a partial positive. If you see it without the partial symbol, that's a full negative. And so that would be the case where the electrons have totally been given up, and maybe it's an ion that has totally dissociated, perhaps in water. So because of these partial charges that we see, this is what we call a polar bond. So a polar bond is just this uneven sharing of electrons. So sharing of electrons is a bond, uneven sharing of the electrons is polarity, or a polar bond. Because we have induced I mean caused, negative charges and positive charges. Now they're partial charges, but they are certainly there. Okay, so that is polarity of water. Now, how do I know that it's going to hold more tightly? So I keep saying that, right? Oxygen wants these electrons a little bit more than the hydrogen, and that has something to do with electronegativity. So you'll recall from your AP Chem how we can determine this, but we're not going to get into that discussion. It has a little bit to do with the size of the atom, which we can't really get into right now. But again, if you're really interested in that, I strongly recommend taking chemistry. But what I can tell you is that aside from the noble gases, we would just exclude this. We don't even want to look at the noble gases. Go away. Not useful for us because they're not reactive. They already have a full valence shell, but again, we don't need to know that. So aside from them, we have increasing electronegativity going to the right. So that would mean the highest electronegativity would be on the furthest right, and we have an increasing electronegativity coming from the bottom going to the top. So because we exclude those noble gases, we can go ahead and look at fluorine and see, okay, well, that is going to be the most electronegative because it is the most top right. Then the trend follows that, then it's oxygen, nitrogen, those are very electronegative atoms. And then we call sulfur and chlorine also electronegative, but maybe not quite as much. They're not quite as selfish as oxygen, fluorine, and nitrogen. So these 5 elements here are going to be the ones that are pretty good at making polar bonds when they are bonded to an atom like hydrogen, which again is not very selfish, willing to give up a lot of its electron. Again, never fully gives it up, but it's maybe holding on a little bit less tightly. Same with carbon, right? These are our biologically relevant atoms that these two are not so electronegative, so they don't really try to tug on the electrons any more than the other ones. But nitrogen, oxygen, and fluorine, very electronegative. Sulfur and chlorine, pretty electronegative. Okay, so we bring that up because we're going to see in our functional groups that we can make some determinations about their properties when we look at how things are bonded together. But when we're talking about water, we know that there's a lot of really awesome properties that come directly from its polarity. And I asked you to name some of those in biology, and you'll get tested on that both on the test and through AP Classroom homework. One of these amazing properties is the idea that water is a universal solvent. And when we say universal, of course, we mean not universal at all, but it is a pretty good solvent. When we say universal, we just mean that it can dissolve a variety of substances, and it's actually very good at it. So that comes from its ability to hydrogen bond, which is caused by its polarity. So when we talk about hydrogen bonding, this is a specific bond that is not a bond at all. So if I look at 2 water molecules like this, where I have an oxygen bonded to 2 hydrogens, and recall that oxygen is electronegative, so it holds onto the electrons a little bit better, so it has a partial negative charge, and my hydrogen has a partial positive, and of course both hydrogens are going to have that partial positive, but I'm going to show you just with the one right now. So on this water molecule, it's identical in all ways. There's no way really for me to differentiate between the two. And so this oxygen as well has a partial negative charge. Well, we know that opposites attract. And so, because opposites attract, these two want to hang out with each other. Because this is a partial positive and this is a partial negative. And so because these two want to interact, we call this a hydrogen bond. It is called a hydrogen bond. Now recall that a true bond is a shared pair of electrons, and I hope that you noticed that I didn't talk about any electrons there. I just talked about an attraction between two molecules because of the partial charges. So we call this hydrogen bonding, not a true bond. But hydrogen bonding is not exclusive to water. Water does it, but lots of other substances do as well. Anything that can induce a polar bond that has a hydrogen in that bond, or as one of the atoms with that bond, can do hydrogen bonding. And we see that on this image here on the left. So nitrogen, recall, is one of those very electronegative atoms, fluorine, oxygen, and nitrogen. It is bonded to hydrogen, so just like oxygen pulls a little tighter on those electrons and has a negative charge, this nitrogen would have a negative charge. And this hydrogen would also then have a relatively positive charge. Now, you might say, okay, but wait a second. This molecule here has an oxygen and a carbon. And you're right. So that sort of is a little confusing to wrap our heads around. But recall that carbon is not very electronegative, so it's pretty willing to give up its electrons comparative to oxygen, who is, once again, selfish. So we have that partial negative charge on oxygen and a partial positive on carbon, and then, of course, that partial positive on hydrogen. And so these guys will associate because of those opposite charges that are attracted to each other. So this becomes really biologically relevant when we start talking about DNA, because it turns out that the bases between DNA are held together solely by hydrogen bonding. And we're going to see why that's really important, and important to know that it's not a true bond, because when we do replication, we need to be able to unwind that DNA. So keep that in the back of your head. Don't worry too much about this test on that, but keep it in the back of your head that hydrogen bonding is not just reserved for water. It can be in any situation where we have a very strong electronegative atom that is bonded to a hydrogen that induces a polar bond, which induces those partial charges and is going to be attracted to the opposite charges in solution. Okay, so we talked about how water is a universal solvent, but really not. It's actually not that universal because it can't really dissolve anything that doesn't have a lot of polar bonds. And so it doesn't want to dissolve nonpolar molecules. And in this case, we looked at this example in class. These are nonpolar bonds because carbon and hydrogen roughly want the electrons the same amount. So these would be pretty even sharing of electrons. So these would be nonpolar bonds. And you can see that all the way through this structure, it will be nonpolar bonds, aside from right here, which this is a carboxylic acid derivative. So we'll talk about this later when we get to functional groups. But yes, this part is polar, but this part here is very nonpolar. That tail, we call that a fatty acid tail, and it is very nonpolar. So water would have a really hard time dissolving this because the nonpolar doesn't have any charges, so the water doesn't really want to hang around it. It's kind of the other way, but we'll talk about that later. Okay, so we have this adage in biology and in chemistry that like dissolves like. And so anytime that there's lots of charges around, partial or not, water really wants to hang out with it, and it'll dissolve those substances. So for sodium chloride, that's a true ion, so that one will actually completely dissociate and become fully charged. And the water will do a really good job dissolving that because of the partial charges all over water. Whereas it would really struggle when there are no charges, where the water just doesn't care. So now we have hydrogen bonding playing a role in some other things. So it's not just how it dissolves, but also how water interacts with itself and other substances that is not trying to dissolve. So we call these things adhesion and cohesion. And if you were in my classes, you might have noticed that I said there's a mistake here, and there is, right? Because this is showing that the oxygens want to hang out together. And that's not true, because these are both partially negative, whereas the hydrogens are partially positive. So really, we should have drawn a hand from this hydrogen trying to hold hands with this oxygen. But I just pulled this off of Google, so it's mistaken. But let's talk about adhesion and cohesion. Adhesion is when water wants to hang out with other substances, it's attracted to other substances, whereas cohesion, co meaning same, it's attracted to other water molecules. So not the same water molecule, but other water molecules. And this becomes really important when we start talking about this idea of capillary action, which is the ability of water to climb up against gravity in situations where maybe if we have a tube that is very, very small in diameter, the water is so attracted to the sides that it will crawl up the sides. But if we compare that maybe to a larger tube, the water is going to be less successful in that because so the surface tension is reduced. Now, this becomes really biologically relevant in certain organisms that don't have muscles like me, for when I want to drink water, I'm able to lift that up over my head and gravity pulls it down. Well, some organisms have to get water all the way from the ground up to maybe 200 feet in the air. So obviously what I'm getting at is plants. Plants are going to be using capillary action to their advantage so that they can get water from deep in the underground all the way up to upwards of 200 feet to their leaves for, of course, photosynthesis. So it's very important to plants, and they've taken advantage of this. This is really quite special. So some of my classes saw this, some of them didn't. It's not that important that you know this. This was just extra information, but you might want to look this up. It is very easy to find. Why Does Ice Float by TEDx. It's not very difficult to understand, and it's a pretty interesting video. So we talked about the polarity of water. We talked about the chemistry of water generally, and we said, well, clearly the chemistry plays a role in how water behaves. Now I want you to start thinking about, okay, the structure of water dictates how it behaves. Same thing for all molecules. The structure of molecules will help predict how it will behave, aka structure dictates function. And this is going to become really important as we start talking about lots of different molecules that are biologically relevant throughout this course. When we get out of this unit, we're going to start talking about bigger molecules, such as proteins and specifically enzymes and the shape of enzymes. The one that comes to my head is ATP synthase when we get into cellular respiration. The structure there is so important, and I want you to keep that in mind, that it's not an accident that these situations arise from chemistry. So important. So we just talk again about smaller functional groups. So these are not very large molecules. We're still talking very tiny molecules. But these are groups that can be attached to larger molecules, and these will have certain behaviors themselves. So a hydroxyl group, when it is on a molecule, it could end up giving it basic properties or acidic properties, depending on the situation. But this hydroxyl group is, as you can see, quite similar to water, so we can predict that this is probably going to be polar. We have that oxygen that would pull on the electrons more than that hydrogen, so it would be polar. The carbonyl here, it's a similar situation. Now, of course, if this carbonyl was attached to a bunch of maybe a hydrocarbon chain, the whole molecule might be nonpolar, but in the case of just the carbonyl alone, this C double bonded to an O, that would be a polar bond because we have a difference in electronegativity. Looking at the carboxyl, well, the carboxyl has this carbonyl right here and a hydroxyl, It's not a mistake, it was named that way. So carbonyl and a hydroxyl are going to be polar as well. So a carboxyl is polar. The amino here is going to be also polar, because remember, nitrogen is also very electronegative. So if we were to replace this with an O, it would just be water. But the amino is going to have slightly different properties. And then the phosphate, as seen here, is going to be a charged molecule, because we see those full charges rather than partial charges. So we don't really call them polar or nonpolar. It's not just a binary system. We have polar, nonpolar, and charged. So all of these become biologically relevant, and you can see where. So carbohydrates all often have a hydroxyl off of them. Deoxyribose has one. Ribose has at least two. Carbonyls, now I told you that the carbonyl itself is polar, but lipids are typically nonpolar, so off of what comes off of these bonds are typically going to be nonpolar substances, like in lipids. The carboxyl is very important for proteins, and we're going to see that on the next slide. Same with the amino, very important for proteins. We're going to see that on the next slide. And then phosphate, maybe you remember the sugar-phosphate backbone of DNA. Well, phosphates become really important for that as well. So this is just scratching the surface, but there are actually two more that we need to talk about. One is the sulfhydryl. So I put these guiding questions here for a reason. So recall that elements in the same group on the periodic table, that's the same column on the periodic table, those tend to have similar behavior. And we can understand why, right? We recall that oxygen is going to make two bonds because it's two away from that noble gas state. Well, sulfur is right below oxygen, so it also is trying to get to the noble gas state. In this case, it kind of wants to look like argon. So it'll also gain two bonds. So that's a similar behavior. And so because of that, a sulfhydryl is also going to be polar. Now, we remember, hopefully from the beginning of this review, that the three very electronegative atoms are fluorine, oxygen, and nitrogen. But sulfur and chlorine were also kind of electronegative. So these will induce a similar polar bond, but it won't be as strong. It will not be as strong as, or I don't want to say strong, but it will not be as polar as an oxygen bonded to a hydrogen, which in that case would be a hydroxyl. The other one we need to talk about is the one special one, right? It's the one that's not polar, because we only have C's and H's. We have no electronegative atoms involved in this structure. And so this one is only going to be the only one that we're really talking about that is nonpolar. Now, we see this show up all the time when we're talking about DNA regulation and epigenetics. So I want you to keep in mind other times it is modifying other macromolecules, but we'll talk a lot about methyl and methylation when we get to epigenetics later in the year, pretty far into the year. Okay, so I told you that the amino and the carboxyl end up being very relevant for proteins, and that's because they are really making up the foundation of the amino acid. So all amino acids are going to have this structure as the backbone. Now, we don't call it the backbone because it's not a very large structure, but this is going to be the same for all amino acids. Now, what's different is this thing here bonded to the middle carbon. So we have this NCC structure that is the same for all amino acids. The middle carbon will have something bonded off of it that is going to be different, and that will tell us the identity of that amino acid. For cysteine, it is the CH2 and this sulfhydryl group. But I want you to also recall that there is the amino group right here. And we talked a little bit about this in class, but maybe this threw you off, that it's H2N. The only reason it's written this way instead of NH2 is because we want to show that the carbon is bonded to the nitrogen, not to the hydrogen. So this is just a nomenclature thing that biologists and chemists agree on. So this is my amino group. This one here when it has the hydrogen on it, is called a carboxylic acid. So it is the same root structure as a carboxyl, but the carboxyl had that negative charge when this OH leaves. But this is called a carboxylic acid. So maybe you're putting it together that this is going to be an amino for the left side of the structure, carboxylic acid on the right side of the structure. So that is why we call it an amino acid, because one side is the amino and one side is the acid. So cysteine is going to be slightly unique because it's one of two amino acids that contain sulfur, but ultimately it's that R group that gives the identity for the amino acid. Then we also looked a little bit at leucine, isoleucine, which is going to be an isomer, which we'll talk about in the next review. But isoleucine also has the amino group because it's an amino acid. This is another way to represent the carboxylic acid group right here. It's not showing the bonding pattern, but this is a shorthand that a lot of biologists will use. And then it has this big R group that is very nonpolar. We can see that it's very nonpolar. And so when we're talking about the polarity of an amino acid, we are typically looking only at the R group because the amino and the carboxylic acid group are going to never change. So we're talking about the R group when we're asking, is that a polar or nonpolar amino acid? In this case, it's going to be nonpolar because I don't see any electronegative atoms in that R group. Okay, that is where we left off in class on this lecture. So I want you to go back to slide, 2, where it talked about all the things that you should know, and if you're able to say it out loud, meaning in English words, then you're in good shape for this unit, or at least this section of this unit. Next, we're going to talk about the macromolecules, and hopefully you'll feel really prepared for this exam. Thank you.